Welcome back to the next video in the Let's Calc series. In this video, we're going to be working through the problem set focused on the product rule. Of course, our work isn't just going to be applying the product rule a whole bunch of times, because of course there's a lot more interesting things to do that just simply are calculus involving the product rule. But we're going to look at some of the most difficult questions on here, as well as those AP free response style questions that are tacked on at the end, including a really hard bonus question that's on there. So without further ado, let's jump into the first. The question we're going to address first comes from the first section, which is simply asking you to apply the product rule itself. Question number 2, though, is going to be the one that we work through. The directions say to differentiate each function and to write each answer in an appropriate form. Keeping in mind that simplifying isn't necessary, although we're going to work through, or I'm going to always demonstrate it simplified as much as possible. So in here, for question number 2, it gives us the function 4 square root of x times cosine of x. And before we look at anything else here, it's worth pointing out that this is definitely going to require the product rule, because we have the function 4 root x being multiplied times cosine of x. So that's kind of my starting point to identify. I recognize that I need the product rule because this is a product of two different functions, and there's no way to simplify them based on what's there. So when I go to perform the product rule and differentiate this function g, we'll get g prime of x. Looking up there then, just kind of using notation, we'll have the derivative of 4 root x times cosine of x plus 4 root x times the derivative of cosine of x. And again, if you're wondering where that comes from, it comes from the product rule itself, that fast, quick to remember derivative rule for f times g of x. That's equal to f prime g plus f g prime. So that is the product rule. You've got the sum of two mismatched products. In other words, you've got a derivative and a function and a derivative, and you have the sum of them. They're mismatched pairs, or mismatched pairs of products. The sum of mismatched pairs of products, something like that. Either way, we're ready to go. So in looking here, we've got to take the derivative. So I'm going to do the traditional derivative rule that I know best, which is that the derivative of square root of x is 1 over 2 root x. And again, if you want to turn this into a power like x to the 1/2 power, that's fine. It's just not the way I'm going to demonstrate it. So this is going to be 4 times 1 over 2 root x times cosine of x plus 4 root x times negative sine of x. Now that can of course simplify. First the 4 and the 2. We'll get 2 over square root of x cosine of x, and then minus 4 root x sine of x. Now at this point, this is technically a correct answer. You could stop right there if you so desired. But I don't like the fact that there's a denominator in one, not in the other, and that there's a radical over here when I feel like we could do something that would clean this up just a little bit. So what I'm going to do next is what some might call unnecessary simplification. But again, you don't know what the form's going to look like on a multiple choice test, so it's good to be able to do this. So what I want to do is I want to get a common denominator. So I'm going to multiply up and down by the square root of x on that second term. I don't need to do anything to the first term because there's no denominator over here. It's just 1. So we're covered safely. So this transforms our function into 2 over root x, or sorry, this will become, let's do this right, 2 cosine of x. Over here we have 4 root x times root x, which is just going to be minus 4x sine of x. And then everything is divided by the square root of x. And now that is another answer that would be perfectly great. In fact, it's a really nice answer. But I do see that there's a GCF of 2 that could come out here. So if I wanted to go as far as possible, I could write this as 2 quantity cosine of x minus 2x sine of x, and then put it all over the square root of x. So if I was going for the most simplified or fullest simplified version, I might go with this one as my answer. You might also see me write, I think in the problem set solutions, the written solutions I did this. This is acceptable as well. It's just kind of your call as to which way you want to go. So in any event, I think the most interesting algebraic thing that happens here is being able to do this move and finding a common denominator. Cleans everything up pretty nicely for you though. Okay, the next problem we're going to hit is a challenging fourth question, which asks you to use the product rule, but not just once, but twice here. We have h of x equal to x over 3 f double prime of x plus x squared f prime of x. So we actually have some derivatives, including a higher order one, built into our function right off the bat. So what I'm going to do here is I'm going to focus on each derivative with a different color to help us identify what's happening. So first, here I'll just do this. So we want to calculate h prime of x, and as we saw, we're going to need the product rule. The thinking for the product rule or behind the product rule is that we've got a linear function times some function f double prime, or the second derivative of a function. We have a quadratic times f prime of x. So So we've got two separate products, so we're going to do the product rule twice. So first, we've got the derivative of x over 3. I'm just going to write that as 1/3 x times f double prime of x plus x over 3 times the derivative of f double prime of x. So there's our first one. And actually, you know what, let's go ahead and simplify that. And I should do this right. I'm going to do this right. Okay, next we're going to add to that, because the product rule does involve a sum of two products. Next we're going to add to that the derivative of x squared times f prime of x plus x squared times the derivative of f prime of x. So there is what we're going to be differentiating. We've got to somehow bring all this stuff together too, if possible, or as much as possible. So let's go ahead and start simplifying. I'm going to start with the green, or the one on the left for those of us who are colorblind. So derivative of 1/3 x is 1/3. So we get 1/3 f double prime of x. On the next one, the derivative of f double prime would be one derivative more, which would be f triple prime. So this will be plus 1/3 x f triple prime of x. Next we're going to add to that. Again, sorry, the color change takes a little bit of time, but I think it's worth it. If you're colorblind, I guess not, but everything else should be good. This will be plus 2x f prime of x, and then it'll be plus x squared times f double prime of x, because the derivative of f prime is, of course, f double prime. Now, at this point, I would probably say that everything is as clean as can possibly be. We're not going to get a whole lot better. But if you wanted to, there are a couple things here. First, let me point out that we have two separate terms that have f double prime. So I might order this, like ordering based on the degree of the derivative. I'd order this as 1/3 x f triple prime of x plus, since we have f double prime of x and x squared and a 1/3, we could write this as x squared f double prime of x plus 1/3 f double prime of x. So we're just kind of getting them close together. Plus the last term, which is 2x f prime of x. Now from here, if you want to simplify anything more, the only things I can really think of here is you could combine like terms, because technically these two are like terms. They're just not that much alike. But before that, I might also factor out a 1/3, just to kind of make it as extremely simplified as possible. In which case we would have 1/3 x f triple prime of x. Over on the next one, we have a 1/3 that came out, so this would be plus 3x squared plus 1 times f double prime of x. And again, my thought process was when you pull out a 1/3, you divide by it here, so we get a 1, f double prime. Over here, we had no 1/3, so x squared over 1/3 is 3x squared. And then both of them have a GCF of f double prime, so I pulled that out in front as well. Finally, we'll have, we had a 3 that came out, or 1/3 that came out, so this becomes 6x f prime of x. And again, this is one of those problems, I'll call this a no winners problem. There's nothing that really finishes and leaves you satisfied. Every possible way of writing this answer is just kind of leaves you feeling a little bit stale. But in a sense, it goes there. It's more important that you can understand how to differentiate all those pieces and recognize that there are two products that you have to attack with. Okay, that brings us to question number 5. Question number 5's directions sometimes mess with people and have in the past, and there's a question just like it with number 6, so I figured I'd start with number 5 and kind of talk about it a little bit more. So the directions instruct us to use the product rule to compute the derivative of each function. Down here it says, in number 5, f of x is sine of 2x, which equals 2 sine of x cosine of x. So what I want you to do is I want you to think of this as differentiating this first function, but since we don't see a product in there, I've provided you a product version of that function. So in a sense, sine of 2x is equal to 2 sine x cosine of x. This is actually an identity from honors pre-calculus or pre-calculus. These two things are equivalent. So if we want to differentiate sine of 2x and find its derivative, we're going to need to differentiate the version that has a product, because we actually know how to differentiate products. So in a sense, this is just kind of your explanation for what the philosophy is behind the question. In a sense, I'm also trying to give you some comfort and remind you of some trig identities, which might actually be helpful. So in here, what I'm going to do, again, I've mentioned this before, I'm going to look at this as a product of two functions. We have 2 sine of x multiplied times cosine of x. And that means that for our particular problem, f prime of x is going to be the derivative of 2 sine of x times cosine of x plus 2 sine of x times the derivative of cosine of x. Simplifying these pieces, we get 2 cosine of x, but times the cosine of x from the original function, and then plus 2 sine of x times negative sine of x. And combining like terms and cleaning things up a little bit, we get 2 cosine squared of x minus 2 sine squared of x. Now this is a very acceptable final answer, except this actually happens to be very much like a particular identity. And in particular, if you factor out a 2, you get that the answer is 2 cosine squared of x minus sine squared of x. And here's the thing. Again, it's probably been a while since you remember, but if you have cosine of 2x, that's the same thing as cosine of x plus x. Cosine of x plus x, using the angle sum and difference identity, we can use the cosine conga. That would be cosine, cosine, sine, 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 cosine, cosine, sine, sine, cosine, cosine, sine, sine, cosine, cosine, sine, sine, sine. So in any event, there is our identity. And what that means is that cosine squared minus sine squared is actually equal to cosine of 2x. Which means once we factor out that 2, you could, if you happen to know this identity, rewrite this derivative as 2 cosine of 2x. Now, it's not essential that you do. I doubt many of you recall that identity, just because it's double angle identities aren't the ones that stick with you the longest. But at the same time, both those answers are there, and it's kind of neat to see that the derivative of sine of 2x is 2 cosine of 2x. And it should make a little bit of sense because the derivative of sine of something should involve cosine, but there's that extra 2 and stuff to have to worry about that. So if that interests you, we'll come back to it in a few days. In any event, though, that answers question number 5. You'll approach 6 in a very similar fashion. Okay, next that brings us to question number 7. 7 is an application question, so we're talking about a particle that's moving along the x-axis. We're given its position function, and they want the velocity and acceleration functions. In order to do this, though, we have to deal with the fact that we have a product. So in other words, we're going to have to use the product rule in order to find the velocity and possibly the acceleration functions as well. So let's put this into action. So what we want first is to note that s of t is 10t squared sine of t. If we want to calculate the velocity, we're going to need to differentiate s. So we want s prime of t. Looking up at our ingredients using the product rule, we'll have 10t squared prime times the sine of t plus 10t squared times the derivative of sine. And of course, these things aren't particularly difficult to evaluate. We'll have 20t sine of t plus 10t squared cosine of t. So there is our velocity. Good job, us. We moved through that problem with great velocity. So everything's good to go. We did the velocity. Here's the problem, though. They want the velocity and the acceleration. So unfortunately, acceleration is going to require us to differentiate this guy. Problem with this guy. Product rule, because 20t and sine are two separate functions. And product rule. So in that situation, again, we're going to need to differentiate and use the product rule twice. Which isn't so hard. It's more or less just kind of a little bit tedious. But we have to do it. So let's jump in. So next we want the acceleration. A of t, we can think of as the rate of change or derivative of v of t. So it's v prime of t. And that's going to be equal to the sum of two product rule derivatives. Oh, look at that, I thought of that. Let's put the plus sign down. So in here, I'm going to do the derivative, or the product rule. We'll have 20t prime times sine plus 20t times sine prime. And again, hopefully you're reaching the point where you're going to be comfortable not doing this first step and writing out each piece. But again, if it's taking you a little bit to get used to it, write it out every time. There's no downside for it except for the little bit of time it takes. Okay, for the second one, we're going to do the derivative of 10t squared times cosine, and then plus 10t squared times the derivative of cosine. So evaluating these pieces, I'm going to cheat and do the one in green first because I already have that pen out. I'm going to have 20t cosine t minus 10t squared sine of t. On the other side of the plus sign, we're going to have, maybe something here will clean up. We'll have 20 sine of t, and then we're going to have plus 20t cosine of t. And with that done, we can now bring in the brown that combines the red and the green. Looking in here, are there any like terms? Yeah, there actually is. I see a 20t cosine t and a 20t cosine of t. To wrap this up though, we want to just combine like terms and crunch it all together. So I'm going to see the acceleration as 20 sine of t plus 40t cosine of t minus 10t squared sine of t. And of course, if that answer is not satisfactory to you because of the presence of a GCF, you could GCF out the 10 and be left with 10 times the quantity 2 sine of t plus 4t cosine t minus t squared sine of t. And that would also be an acceptable version of your acceleration. So in any event, the real challenge here isn't the application. The real challenge is having to use the product rule multiple times. In a sense, to get to the acceleration, we had to use the product rule 3 separate times, including twice in our final calculation. So just something to keep in mind and be on the lookout for. A little bit of a challenge, but not hard if you just keep your work organized, maybe even think in different colors. Okay, that brings us to an AP style question focused on a table of values. So we're looking at things numerically here. Imagine there's going to be a little bit of product rule mixed in there as well. So in question number 9, to go along with this table, it says let f and g be continuous differentiable functions. We haven't talked about what differentiable means, but it means you can basically take a derivative anywhere. So for now, it's not going to affect our problem, but it means that the derivative exists everywhere in these problems. You're never going to run into an issue where you can't calculate a derivative. Just know that. Next, it says values of f and g, as well as their derivatives f prime and g prime, are given in the table below. Then it asks us to use the table to answer the questions below. So we're going to answer A through D here. So the first question says, consider k of x equal to 5g of x minus 3f of x. Compute k prime of 5. So in order to do this, we need to compute the derivative of k. In other words, we're going to differentiate with respect to x that expression they gave for k, which is 5g of x minus 3f of x. And this isn't particularly difficult. We're using the scalar rule as well as the sum and difference rule. Derivative of 5g of x will be 5 times the derivative of g, which we know is g prime of x. For the second one, we'll have similarly minus 3f prime of x. So there is k prime of x, but of course we didn't want k prime. We wanted k prime of 5. So looking up at our pieces, we need to calculate 5g prime of 5 minus 3f prime of 5. Those values for g prime and f prime of 5 should be in the table. For instance, g prime of 5 is going to be right here. So k prime of 5 is going to be 5 times negative 9. And then we'll do minus 3 times f prime of 5. And again, reading the table carefully, there's the f prime. F prime of 5 is 2. So combining this information together, we'll get negative 45 minus 6, which is negative 51. So k prime of 5 is negative 51. So not particularly difficult. Not even using the product rule here, I might point out. So don't go too crazy and don't get too upset about it. But this is the sort of like abstract differentiation work you might have to do. Okay, next, this brings us to question 9b. Let h of x equal 2f of x g of x. Very standard product rule kind of problem. How can I tell? I see 2f of x times g of x, so I see a product of two functions. So if we need to differentiate all, we're going to have to use the product rule. Next, it says write the equation of the tangent line to h of x at x equals, negative 3. So in here, if we want the tangent line at x equals negative 3, we need two things. First, we need to calculate h of negative 3. So we need the actual y value that's going to be there. Well, plugging in, that's going to be 2f of negative 3 times g of negative 3. Looking over at our table, f of negative 3 is going to be negative 4. And g of negative 3 is going to be 7. That's going to be negative 8 times 7, which is going to be negative 56. So that is going to be our y1. Of course, negative 3 is x1. And we're thinking y minus y1 equals mx minus x1. So we got the y value. We already had the x value. The challenge here, of course, is finding the m value, the slope. So we want to calculate h prime of x. And again, we're using 2f of x times g. So using the product rule, that'll be the derivative of 2f times g plus 2f times the derivative of g. So simplifying a little bit, that's pretty easy to calculate. 2f prime g plus 2f g prime. But of course that's h prime of x. We want h prime of negative 3, so we can get the slope specifically at this point. So that's going to be 2f prime of negative 3, g of negative 3, plus 2f of negative 3, g prime of negative 3. And again, the challenge here isn't that this is particularly hard. It's basically 2 times the product rule. The challenge is now that we have all these pieces, we have to pull the right information out of the table. So let's do it carefully. We have 2f prime of negative 3 is 5. G of negative 3 we already had is 7. Next we got the 2 again. We have f of negative 3. Once again, that's negative 4. G prime of negative 3 hadn't been used before, is negative 6. So as far as the value of that slope, we have 2 times 35 is 70. Then over here we're going to have plus 24, 48. Okay, looks like that's going to give us 118. So our slope is 118. Our y value, this is going to be our m value, sorry. Our y value was negative 56, our x value is negative 3. So without any further ado, our tangent line is going to be y minus a negative 56 is equal to 118 times x minus a negative 3. And there is the tangent line we were looking for. Okay, that brings us to question 9c. Now 9c is asked in a way that we may or may not have covered in class. We used to in the past. I may have changed things around a little bit. So I just want to make sure to go through both 9c and 9d very carefully with you and kind of explain the philosophy. But in question 9c, we are asked to estimate the value of g prime of 7. So in looking at this question, an important thing to consider first is that we can't report out and compute the value of g prime of 7 itself because we were only given values of this table at x equals negative 3, x equals 5, and x equals 9. 7's just not in the cards for us. We just didn't get that one for free. So we can't compute g prime of 7. All we can do is estimate it. And the idea here is that in order to estimate the value of a derivative, we can estimate that what we'll call f prime of c using, and of course, how can we approximate a tangent line slope? Well, we can use a secant line. So we can use the average rate of change, which we know as the slope of the secant line. Use the average rate of change on an interval with x equals c at the center. So in other words, if we don't have enough information about the function to compute its derivative at a given point, we pick an interval surrounding that point, and then we calculate the average rate of change on there. And we get as good an estimate as we can possibly can, especially with the limited information we're provided. So looking on here, we're supposed to do g prime of 7 approximately equal to something. Looking at our points that we are given, we have x equals negative 3, we have x equals 5, and x equals 7. Well, notice, in the middle of 9 and 5, in other words, the average value of 9 and 5 is actually 7. In other words, 7 is the center of that interval. So using the average rate of change on that interval should be as good an approximation as we possibly can use. So for this case, what we're going to do is we're going to calculate the average rate of change on the interval from 5 to 9, because that should give us a good estimate of the derivative at 7. So in our case, that means we're going to use g of 9 minus g of 5, all divided by 9 minus 5. And then from here, it's just looking in the table. G of 9 is negative 1. G of 5 is 0. Well, thanks for that. 9 minus 5 is 4, which means the average rate of change is negative 1/4. And more importantly, that is our approximate value of g prime of 7. So all we did was use the average rate of change on an interval using that particular value, and we were able to calculate it. And then last thing, notice, to approximate g prime, we don't use g prime, we use just plain old g, because this difference quotient is a lot like slope. So if we want to approximate the slope, we use the function itself to do y2 minus y1 over x2 minus x1. So keep that in mind as well. Along the same vein, in 9D, you're asked to estimate the value of f double prime of 1. So once again, we're going to use the same technique. We're going to approximate it using an average rate of change on an interval containing 1. Well, looking up on here, 1 is between -3 and 5. And in fact, if you add those up and divide by 2, you'll of course get 1. So it makes sense that we're going to use the functions on those intervals. But the difference here is because we want to calculate an estimate for f double prime, we're going to have to use the derivative itself, f prime, because that way we'll be approximating one derivative down. Just like before, when we did the problem, we had g prime approximated by g. F double prime will be approximated by f prime. So in other words, this will be f prime of 5 minus f prime of -3 all over 5 minus a -3. As far as values then, we can pull them out of the table. F prime of 5 is 2. F prime of -3 is 5. Do that right? Yep. F prime of -3 is 5. Yep. And then divided by 8, we're going to get -3 over 8. And so once again, if we're approximating those guys, we use one derivative down. That way we're able to take care of everything. Heck, if we wanted to approximate f triple prime, we would use f double prime and an average rate of change difference quotient. So a little bit different, a little bit weird, but not difficult to do. Something important to remember, average rate of change approximates the derivative. In fact, I'll write it right here. Average rate of change approximates derivative. It's a good thing to know for sure. Okay, next, that brings us to the massive question at the end, 10. 10 gives you a piecewise linear function, and then it asks you to use that graph to answer the questions. So in here, let's see. Normally I would write out a piecewise function for that L of x over there, and this is, of course, L of x. I'm going to choose not to just for the sake of time. Hopefully I won't have to find every single piece. I probably will, but we'll find out. So it says let p of x equal x squared L of x. Write the equation of the tangent line to p of x at x equals 2. So in here, a couple pieces. First and foremost, if we want a tangent line, we need p of 2 and p prime of 2. P of 2 is going to be 2 squared L of 2, which is 4 L of 2. And looking over at our picture, L of 2 would be right here. Now, of course, it might not be right on the line, but looking at the graph, it looks like we go up 4 over 2, which means we also go up 2 over 1. So there absolutely has to be a point right there, which means that L of 2, I'll even write it here, L of 2 equals 2, 2. So that makes this 4 times 2, which is 8. And that's going to be our y1. Next, we need p prime. So let's first calculate the derivative. We're going to have x squared prime times L of x plus x squared L prime of x. I should have just done this one faster. This gives us 2x ln of x plus x squared L prime of x. And then specifically we're interested in p prime of 2, which is going to be 2 times 2 L of 2 plus 2 squared L prime of 2. So looking at our equation here, we already established that L of 2 is equal to 2. So that means this is 4 times 2 that we'll be calculating. Next we have 4. And then we want L prime of 2. Well, looking at L prime of 2, that's the slope. Well, that slope is clearly up 4 over 2, or up 2 over 1. So L prime of 2 is also 2. It's a lot of 2. I feel like I'm watching a ballet recital here. So many 2-2s. Is that funny? Maybe? I don't know if people even wear tutus in ballet past the young ages. So in here we have 4 times 2 plus 4 times 2, which is 8 plus 8, which is 16. That is our slope. To write our tangent line then, y minus y1 equals mx minus 2. So again, nothing too crazy. Did have to use a little bit of analysis of that piecewise linear function, but otherwise things work out pretty nicely, if I do say so myself. Okay, it takes us to B. Compute the average rate of change of L of x for -1 to 11. You can be sure, having been asked lots of average rates of change questions over the last few days, you can probably expect this one must involve some sort of trick, or else I wouldn't have asked it again. So looking at our picture, we have to figure out what's happening at -1, which is very inconveniently some awkward number on that line, so we'll have to play with that. And then we also need to figure out what's happening at 11, which is somewhere off screen. So it's somewhere that way. So we got some issues to deal with here. First, though, of course, the average rate of change is going to be L of 11 minus L of -1, all over 11 minus a -1. And you might ask why I write that here. And the reason is, if I were taking an AP exam and this was a question, which it might be, it could be, I would get a point for writing the difference quotient, or I could potentially get a point for writing the difference quotient. And if you ran out of time or just got caught up in trying to do all the rest of the work, you'd at least get that 1 point. Whereas if you waited till the end, if you ran out of time and never wrote it, you never get any points either. So keep in mind it's good to write down what you have. It also reminds us that what we need is L of 11 and L of negative 1. So from here, let's look at each of these pieces independently. First, L of 11. So our graph only goes from -5 to 5. But the thing I see here is that it appears that the function becomes constant for x values greater than 3. So in fact, I'm going to say that. From there, L of x is equal to 4 for any x value greater than 3. And what that tells us is L of 11 is equal to 4, which is nice. That's an important piece of information for us to plug in over there. In fact, we've now got 4 minus something over 12. Our big problem is now we have to figure out what's happening with L of negative 1. So in a sense, it's there. So what we need to think about is what is happening with L of x in that region. So looking up at our picture, we're interested in what's happening from -2 to 1. It's this line that's right there. Looking at our picture, I see a couple things. First, I see it's a line, so that's going to mean it's mx plus b or something close to it. We could also use some sort of other notation. In fact, let's do this. Let me go ahead and think about that. L of x, the equation of that line. We're going to have y minus something equals slope x minus something. So first, let's do the slope here. We can just count out the slope. Down 2 over 1, 2, 3. So it looks like the slope is -2/3. From there, we need a single point to define this line. I'm going to choose the point right there. It has x coordinate 1, y coordinate 0. And what that means is L of x is equal to -2/3 x minus a -2/3 when x is between -2 and 1. So with that in mind, if we want to calculate L of -1, that's going to be equal to -2/3 times -1 plus 2/3, which is, 2/3 plus 2/3, which is 4/3. So with that in mind, we now know that L of -1 is 4/3. So as a heads up, if you were out of time, you could just circle that and that would be your answer, and it would be correct. But of course, I settle for nothing that small. I settle for nothing less than the final bestest answer. So in here, looking at our ingredients, what I see is this is 4 minus 4/3 all over 12. I'm going to find a common denominator. That's going to give me 12/3 minus 4/3 all over 12, which is 8/3 over 12, which is 8/36, which is 2 divided by 4 divided by 4 ninths. And there is our 10B. Everything looks like it's working pretty well. Looks pretty comfortable. All good. Okay, that next brings us to 10C. 10C is a whale of a question, moo. And looking at that question, there's just a lot going on in here. So it can be a little intimidating to start with. What I'm looking at, though, is some sort of definition of the derivative situation. And the reason I see that is because I've got some limit involving h's, and I've got some functions that are kind of plugged in there a little bit. So in looking here, because of that h, my first thought is to think about the definition of the derivative, which says that f prime of x is equal to f of x plus h minus f of x all over h. And that would be equal to f prime of x. In fact, I shouldn't say equal, it's kind of directed there. So in looking here, of course, there are a couple issues. On the limit on the left, there's not a single x value in there because it's already been replaced. So specifically here, and I'll actually even erase this just to kind of show you, I'm going to point out that this has replaced all the x's with a particular x value. And in looking up at our limit, I think you can actually see that that x value is -4. So this is really f of -4 plus h minus f of -4 all over h, and that's all equal to f prime of -4. So we're actually calculating the slope of a particular function at x equals -4. So keep that in mind as you're looking, because now our job is to figure out what is the actual function that's being differentiated. And according to this information from the derivative, we should be focusing right here. But in this case, we need to kind of pretend that there are x's instead here. So it looks to me like the function we're differentiating, I'm going to call it f of x for no reason than just for simplicity. Looks to me like f of x is 3x L of x. So again, keeping in mind what we were doing is we were looking for the structure of the derivative. We found that it matched the definition of the derivative because of the h's. Using that, we also figured out that -4 had been plugged in, so we didn't want f prime of x, but f prime of -4. And from there, we were able to draw out the information and figure out what the function was that's being differentiated in that limit. Now that we have it, of course, we want to eventually calculate f prime of -4, so we first need f prime of x. This, of course, requires the product rule. I can tell because we have 3x multiplied times L of x. So I'm going to do this quickly, and I won't. I haven't done any quickly here. I'll be as careful as possible. So 3x prime plus L of x plus 3x L of x prime. Simplifying here, we get 3L of x plus 3x L prime of x. And now specifically, we're interested in what's happening at -4. We talked about that earlier in red, so let's put it in. So we want to figure out what's happening here. We want f prime of -4, the value of this limit, which will be 3L of -4 plus 3 times -4, L prime of -4. So -4 occurs right over here. Oh, look at that. Someone has blessed us with the y value plugged in on the graph, easy for us to see. Who could have done such a generous thing? Well, now that it's there, we can plug in some information really easy. First, looks like L of -4, according to this picture, is going to be -4. So that's 3 times -4 minus 12 times L prime of -4. Let's see, L prime of -4, according to this picture, we go up 1, 2, 3, 4, 5, 6, and over 1, 2. So L prime of -4 is 6 over 2, also known as 3. So in looking here, we're going to get -12 minus 36 equals -48. So again, that was a pretty complex question. A lot of stuff in there, especially with that -4 plugged in, made it a little bit harder. But we were using the definition of the derivative. Just turned out that the function that we were defining with that limit was actually a function requiring the product rule to differentiate. So we did that, read our graph. Everything turned out nicely. Okay, and the last question on number 10, before we get to the one calculator question, is a bonus question. As it says, this is an optional bonus question. I thought of this right before I went to bed last night, and then overnight I thought about it and went, oh, that's really, really hard. And then I did an evil maniacal laugh, and I felt like, leave it on there. But I'll make it optional so that way people don't stress too much. So what this says is they say let q of x equal 3/4 x squared. So cool, what a nice thing, it's a polynomial, cool. It then says the graphs of q and L have parallel tangent lines at 2 x values. So we've got this phrase that we've probably never read before, which says parallel tangent lines. So before we dig any further, if we have two lines that are parallel, if we have parallel lines, I'm going to spell it correctly this time. I've had trouble with that today. If we have parallel lines, the question to ask yourself is, what does that tell us about the two functions? What property do they have in common? And I hope you know that they have the same slope. Because, of course, if two lines are parallel, they're never going to touch, which means that they have to stay away from each other and grow at exactly the same rates, just through different points. So same slope in calculus terms is equivalent to the derivatives, q prime of x and L prime of x, being equal. So what we want to do is we want to solve this equation. We want to figure out when is that true. So a couple of these pieces could be easy. In other words, we need to know what q prime is and what L prime is. Well, q prime is simple enough. Q prime of x is just 3/4 times 2x, also known as 3/2 x. L prime of x, though, on the other hand, is not so simple because we have a piecewise linear function. It literally says it right here, piecewise linear function. In fact, I'll change color just for simplicity. We have this massive piecewise linear function with 1, 2, 3, 4 different lines going. But we need to know its derivative. So what I'm going to remind you is that if you have a piecewise function, the derivative is just the derivative of each part of each equation in the piecewise function. Jeez, it's hard to say. I don't know why it's so hard. I've been doing this a while. So in here, we need to figure out what the derivative is for each part of this piecewise function. But the nice thing is, every single part of this function is a line. So the derivative, fancy pantsy grey poupon, is really just our slope of each of those line segments. So in looking here, before I do that, that's going to be the fun part. Let me just set this up. Looking at our divisions here, I'm looking at every place where there's a boundary where the line changes. We're going to have x values less than -2. We're going to have x values between -2 and 1. We're going to have values between 1 and 3. And we're going to have values greater than 3. And in fact, look at that. My little curly bracket isn't big enough. Let's fix that. Okay, so now all we need are the slopes. Because again, it's the derivative of each of these line segments that form the piecewise function in the first place. So the first line segment is right here. We found earlier that slope is up 3 over 1. So this derivative will be 3 when x is less than -2. Next, we look at the slope from here to here. That slope is down 2 over 3. So the slope there will be -2/3. The third section runs from here to here. I think we did this one in one of the first two parts of the function. We go up 2 over 1, which means our slope is just 2. And finally, at the very end, if the function is a constant 4 all the time, its slope is 0. So there is our derivative. So we've now found L prime and Q prime, but we're supposed to somehow set these two equations equal to each other. That's not easy. So what I'm going to do, though, is I'm going to attempt each one. It does say there are only two values, so some of these should give us false values or mistakes. But I'm going to set the derivative Q prime equal to each of these slopes, and then check to see what x value comes out, to see if it's in the interval on that section of the graph. It's the only way for us to approach this question. So for instance, if Q prime equals L prime of x, then 3/2 x would be equal to 3. If that's true, that means that x is equal to 2/3 of 3, which is 2. But x was supposed to be less than -2, and 2 is not. So this one does not provide us a value. There's no place on the interval x less than -2 where the derivatives are the same, meaning there's no place where the tangent lines are parallel. Next, let's look at the second one. -2/3, we want to do 3/2 x equal to -2/3. Solving that equation, we're going to get -2/3 times 2/3, which means x is equal to -4/9. Now, -4/9 is like -0.444. The question is, does this fall on the interval from -2 to 1? And oh, absolutely it does. -2 is less than x is 1. That is true. So we found our first value. This is one such value. Our second one will be when Q prime equals 2. That leads us to x being equal to 4/3. And 4/3 is also definitely between 1 and 3. So there is our second value. We've now found the second. So now theoretically, it told us that there were both x values, so that meant there were only 2. But if you wanted to check it, we could always check the third one. I think you'll see very quickly, though, that if 3/2 x equals 0, that means x equals 0, but x is greater than 3 there, so nothing. So instead, we found our two values, -4/9 and 4/3. And again, this is a tough question, especially because you have to construct the piecewise function for L prime. You have to set a bunch of equations equal to each other and check domains. This is a question where I really feel like I've outdone myself and come up with something creative. This is what my mind thinks when I'm having trouble walking and sleeping. So there it is. Again, optional bonus question, but if you can do this, ooh, you're in good shape. So there you go. There is 10D. And last but not least, we have finally question number 11, the final late addition to this problem set. Wanted to do something involving the graphing calculator. I felt like it was an appropriate thing to do. But know that this is a pretty challenging question as well, though one that I think you should be able to do. So first and foremost, it says let h of x equal blah blah. That is, it's not my favorite kind of function in the world. That's pretty involved. There's a lot of stuff there. As of right now, where you're at, we don't have the ability to differentiate this function. So that alone tells us that we're going to need the calculator. Next, it says let j of x be such that j of 4 equals -3. Oops, and that's supposed to say j prime of 4. So we'll fix that on the assignment. So we have j prime of 4 equals -3. Then it says if m of x equals h of x times j of x, and m prime of 4 equals 3/5, find j of 4. Okay, we're gonna go through this as much as possible. So where can I start? So I'm going to start here. It says m of x is h of x, j of x, and m prime of 4 equals 3/5. So what I'm going to start with is I'm going to try to calculate out what m prime of x is equal to. So let's just start there. M of x is h of x, j of x. That means that m prime of x, which seems to be involved in the work we're doing, is going to be h prime j plus h j prime. And more specifically, m prime of 4 is going to be equal to h prime of 4, j of 4, that thing we're supposed to find, plus h of 4, j prime of 4, that thing we were given. So a lot of stuff happening here. Let's do, we also have one more thing. It says m prime of 4 is equal to 3/5. So this whole thing is going to be equal to 3/5. And you know what, I'm not going to write it there. I'm just going to carry it through to the next line. Okay, so in looking here, we've got a bunch of different pieces. J of 4 we don't know. So here, carrying along for the moment. J of 4 is a mystery to us. But J prime of 4 is going to be -3. So I'm going to write this as minus 3 h of 4. So there's where we stand. Looks like we have three things missing. H prime of 4, h of 4, and j of 4. But look no further than right up here. So keep in mind, we were told that h of x is equal to this complicated function. So I'm thinking what we should do is we should go figure out the values of h of 4 and h prime of 4, and then figure those out. Because once we have those, if we have that and that, we'll only have one thing left to solve for. So let's use our calculator to grab that info. So where is my calculator? There's my calculator. There we go, stick it right there. So a couple things here. First, I'm going to put in this complicated function, h of x, into the calculator, and then I'm going to store it as y1, so that way it's easier to work with. So in here, though, we don't have a fifth root button. Well, technically, yeah, we do have a fifth root button, so let's just show it. So the fifth root button is right down here. You could otherwise, by the way, use the 1/5 power, but for the moment we do have a fifth root button. It's right there. So if I go down to math 5, it gives me this option. So I'm going to put a 5 in. Inside here, we're going to have 3 sine of x plus the square root of x. And although we don't have to close the parenthesis, I'll do it just for safety. Okay, so there is y1. That y1 is now playing the role of h. So a couple things. First, we need to know what h of 4 is. That's straight up plugging 4 into the function. Well, we could do that just by doing the fifth root of 3 sine of 4 plus square root of 4. Or we could again do alpha trace y1 parentheses 4. And that will give us our correct value of negative 0.9653. And of course, there's a lot of decimal accuracy here. So if I'm going to do this correctly, I should really be carrying all of these decimals as far as possible. So there's a problem though. If we want to put this into our actual function, it's going to be a huge mess to have to carry this many decimals in. And again, I didn't make it clear a second ago, but we can't we can't short ourselves any of these decimal places because intermediate calculations need to be exact. So what I'm going to do is I'm going to actually take advantage of the calculator's ability to store things as under different names. I'm going to let the calculator take this value we just found, and I'm going to tell it to store. That button is right there. Notice it just highlighted in red. I'm going to ask it to store that value as alpha A. Then when I press enter, if I want to recall that value on the calculator, I can just pull up the letter A, and voila, there it is. So in here, I'm going to literally say that's equal to A for my calculations purposes. It'll make our work a lot easier, and it'll be just like we do in our calculator. Second, I want to calculate h prime of 4. I'm going to go to math 8 this time. I'm going to do the derivative with respect to x. We want to calculate it at x equals 4. And I want to do it for the function alpha trace y1. This will now give us h prime of 4, which is 0.82930. 829. Did I say 9? Gee, it's hard to remember these pieces. 8293048. And there's more decimal places, but again, I don't want to carry all those numbers. I don't want to have to write them again, and I also don't want to cut out any and get the answer wrong. So I'm going to store that in my calculator as another variable. So once again, I'll press store, or stow, alpha b, and enter. So I'm going to now call this b. So now I've just redefined the problem. I've given myself the two values that I need. Now my job is to finish this off. So in looking over here with our new values, we have 3/5 is equal to h prime of 4, which we called b, and then j of 4, which we don't know. So we've got to multiply those two by one another. Then we've got minus 3 times h of 4, which we're going to call a. And now we just need to solve for j of 4. So moving some stuff along, I'm going to add 3a to both sides. We're going to get 3a plus 3/5 is equal to b times j of 4. And last but not least, we'll just divide both sides by b. So in other words, our function value, j of 4 that we want, is equal to 3a plus 3/5. You could also write that as 0.6 all over b. And for our purposes, we want to have our approximate final answer. So once again, I'm going to pull out the calculator, move it to the side a little bit here. We're going to have, jeez, this is messy. We're going to have 3 times a plus 3/5 all divided by alpha b. And make sure it looks right. Again, I don't get to use my glasses on here. Gives us our value of negative 2.769. Or we could go with the approximate value I think was there. Negative 2.768. And with that said, that difficult problem, another probably I'd consider it almost like a plus question here. With that said, you've now seen everything from the product rule assignment. Hopefully this has been as informative as any video you've seen up to this point. Hopefully it supported you in your work. And as always, thank you for watching. Have a great night.